So here we have a structure. Again, we use Moly radiation. The I over sigma is 50.8. Very good data. R-int 5.2, not bad. And we have 99.8 completion. One thing you may notice is that the space group is I2 upon A. We'll go with this space group for now, but maybe when we do a checksif, it may suggest it's a C-centered. So I2 upon A and C2 upon C. You know, if it's I-centered, you can actually convert it to C-centered as well. And so for now, we'll deal with the I2 upon A and then see if checksif denotes any additional symmetry. And we can also try to, you can also use, once you solve it in I2 upon A, you can actually use Platin to convert it to C2 upon C if it works. But for this exercise, we'll leave it in I2 upon A. So we go to solve. Notice here that we have carbon. I forgot to click the arrow, but we have carbon, hydrogen, boron, and oxygen. And so if I click on the solve button, I use SHELX. We use I2 upon A. Now, in addition to I2 upon A, it also gives us the structure solved in IA if you want, or I2. So for example, if you think it's IA, you can click on that and it will switch it. Oh, well, it should switch it to that particular space group. So there was an error here. Let me try to solve it again. Well, you should be able to click on the space group and it'll give you the space group, the structure in that particular space group. For some reason, it's not doing it for me, which is okay. So here I2 upon A is our space group. Now it has boron, oxygen, and carbon. And so I didn't give you a picture of what this structure looks like, but the oxygen's here. And here are the correct position. So there should be 2 oxygen atoms here. And we should see also 2 oxygen atoms here and here. So if I was to give you a proposed structure, these 2 positions should be oxygen atoms. So let me go ahead and change this one to an oxygen atom. Now this one that's labeled a boron, well, obviously boron can't have 4 bonds attached to it and still be neutral. So this should be a carbon atom. So I did say there was boron in the structure, but for now, let's not label anything boron and see if the thermal parameters of some of the atoms will manifest itself and say, hey, there should be a boron here. Now we go to refine. Make sure you have your ACTA and your refinement program. So nothing too out of the ordinary. One thing to notice is that there's some heavy electron density peaks near the oxygen atoms that we may have to account for later on. Get it to converge. Now let's do anisotropic refinement. So I'm just refining for it to converge, to shift. It's taking its sweet time. One more time. Let's see if we can get it. Alrighty. So notice here that these two oxygen atoms, so these over here look nice, shaped thermal ellipsoids, but these over here, very elongated. So that means there's some disorder in this oxygen atom because it's vibrating or it's going up and down. It's stretched, looks like a cigar type thermal ellipsoid. And if we look at the top of it, we see there's a heavy electron density peak. So this may indicate that maybe this oxygen atom is disordered. So what I'm going to do to start with is I'm going to take this oxygen atom, set its occupancy to 1/2, and then that Q peak right above it, I'm going to set to make it an oxygen atom and also set it to occupancy 1/2. Now remember, since these two are the same oxygen atom but on disordered positions, we're going to set the top oxygen atom as part 1 and the bottom one as part 2. That way they're not bonded together. They're two different, the same atom on two different positions. So now we click refine. And we see now this one went to a very small ellipsoid. So we made it, maybe it's more occupancy than what we gave it. So let's go back and move this to say 60% and this to 40% and see if that helps the structure. So not bad. Now the ellipsoid is fairly shaped. Again, the other oxygen atom is a little bit elongated, but right now we don't see a big enough electron density peak next to it. So you see the main electron density peaks are hydrogen atoms. So what I'm going to do now is I'm going to add hydrogens to get rid of all of those so I can focus on any major discrepancies. So you see here Q1 is the largest Q peak, and it's off of this oxygen atom here. So what I'm going to do is I'm going to change the occupancy of this oxygen atom to 1/2, label this as an oxygen atom, and change it to 1/2 to see if that helps with the thermal ellipsoids. Now notice that the one that's sphere we labeled as part 1, so this one we're going to label as part 1. And then the one that's the thermal ellipsoid we're going to label as part 2. So again, here you see that it's the one that was already a thermal ellipsoid is quite small, and the sphere is quite big. So we're going to change this back to 60%. Which is in line with this one over here. So now these two are 60%. and these two are 40%. So it's like a 60-40 split. And we're converging the shift parameter a little bit faster now that we've modeled that disorder in the oxygen atom. So now if we want to change these to anisotropic, select both of them and go anisotropic selected. And so this is a little bit bigger compared to the other atoms. So there may be some something here that we may have to look at if we get a checksif error on the on that atom. So now if we look at this methyl group, doesn't look that bad. So let's go ahead and add some hydrogens. Now we can look at the reflection data. So you see here, even out past 50 degrees to theta, we have very strongly diffracting data. So again, I'm going to set it to about 55, the cutoff. And so in the second set of instructions, omit -355. We can update the formula. Info, let's check bad reflections, still good. And we can now look at the weighting parameters. So I'll go ahead and use the suggested weighting parameters here to start off with. And let's refine it. You see here, the second weighting parameter is quite large. So maybe there's something wrong with our structure, maybe, or the data quality. So now let me go to report. There again, this was a clear colorless crystal. Let me see if the I forgot to write the all right. So we'll just put some values here for now, 0.3. I have them written down somewhere, but for this exercise, we'll just put them in. Nylon loop. So for here, the diffraction temperature was 98 Kelvin. And it's already got the absorption correction. So we hit refine. So what I want to do is I want to first do a checksif before I start messing with the weighting parameters anymore to see if there's any systematic error with the data. So I'm just waiting for the checksif report. Taking its time. So with the alert level B, it's saying one of these thermal ellipsoids is large compared to its neighboring atom. So maybe we have the wrong atom type. And then with these alert level C's, it's saying, especially the first 4 are kind of mentioning that, hey, we have this large electron density peak. Check to see if it's a relevant atomic site. So we'll take a look at both of these and see if we can address each one of these issues. So let me switch back to OLEX. So it was C00P. Oops. So this is C00P, and its thermal ellipsoid was smaller than O002. Now, both of these oxygens are single bonded oxygens. If we look at the bond distances, 0.36, 0.46 bond distance. Over here we have 1.469, 1.369. So these are fairly long single bond oxygen atoms. And then this carbon-carbon is a single bond as well. So what I'm trying to show you is that if this is a carbon and we have 3 single bonds, well, then what's missing from this carbon atom? If it has 3 single bonds, it must have a hydrogen atom. And so what we can do is we can see here, hey, is there a hydrogen atom off of this, atomic site? And if the answer is no, maybe this should be a boron atom. If the answer is yes, then it's a carbon atom. But if it's no, it's a boron. So what I'm going to do is I'm going to go back to refine, and I'm going to increase the peaks to see if a hydrogen atom pops up at that near that carbon atom. And the answer is a resounding no. So this tells us that this position is a boron, because remember, boron can have 3 bonds, 3 single bonds around it. So what I'm going to do is I'm going to change this from a carbon to a boron. And since this is a kind of a mirror image of both sides, I'm going to do the same thing to the other side as well. Because the only difference between these sides is that these oxygens are disordered, these are not. And so that kind of disrupts the symmetry in this structure. So if these were both ordered oxygens, both sides, then there may be some symmetry within the molecule. But the fact that it is disordered kind of breaks that symmetry. So now let's refine. If we see a positive result, aka our R value gets better, that tells us we went in the right direction. So let's refine here and see what happens. So see here, our R value lowered, even our goof lowered, so we don't need as high of a goof as we need. So let me update the formula. Let me update the weighting parameter, refine again. So it's looking good. Now the other error that we were dealing with was this electron density peak near this carbon, because this is the highest one. It's saying, hey, you need to address and determine what this could be. And so one thing it could be is that this methyl group is disordered. So maybe, remember this oxygen O1 is 40% occupied. Maybe this carbon here, this electron density peak, represents a methyl group that is 40% occupied. So what I'm going to do is I'm going to right click, change this to a carbon. And this is okay. You see how it bonds this here? Well, remember this is part 2. So this methyl group will be part 2. And remember part 2 is 60% occupied. So we're going to change that to 0.6. And then this carbon atom goes with this oxygen atom, which is part 1. And part 1 is 40% occupied. And so now if we refine, let's see if we have a better result. And so let's see. So obviously this needs to be a little bit smaller. This is 40. This is 60. Maybe we do 65%. 35%. Now let's do an anisotropic on this one. Not bad. Still looks a little, it looks all right. Now let's add some hydrogens. There we go. We were just missing the hydrogen atoms. So now this one, it looks a little small, but it's okay. Maybe we could increase this to 70%. Increase this, decrease this to 30%. So again, it's just going back and forth, tweaking these occupancies. I didn't change it much, but now the ellipsoids look more even, I guess you call it. So since we moved this to 35, let's do these as 35 as well and see if that helps those ellipsoids. And this to 65. It's slightly better, and the ellipsoids look a little bit better as well. So maybe it's a 65, 35 disorder. But the thing is, if we got rid of that heavy peak, so that error that we saw should be gone. And so right now I'm just messing with the weighting parameters and getting you know, the final R that I want. We can check bad reflections. There's really no bad reflections in this data. If we look at the data plot, you know, most of it looks like a linear trend. So there's no reason, there's no outliers to remove. So that's good as well. So I might go in and manually update the weighting parameters. Let me do this here. work, refine. So that looks good. So let's do one last report. See if we have any outstanding errors that we need to address. So one thing we need to correct is the Z value should be 8 instead of 4, because remember this is eye centering. So if we set a Z value of 4, that would imply that there's a half of unit in the asymmetric unit, aka maybe a half a molecule in the asymmetric unit. But since there's a whole molecule in the asymmetric unit, our Z should be 8. So that's one thing we need to correct at our at our checksif file. So Z calculated is 8. Reported calculated as 8 and reported as 4. So we need to change this to 8 because Z prime needs to be 1. And if we scroll down, you see we have no alert B or A error. So that one B error that we saw was in reference to that atom site should have been a boron and not a carbon. And we confirmed that because there was no hydrogen electron density peak for a hydrogen off of that carbon. So now let me go back to OLEX. So one thing we need to fix is the Z value. So we go to edit instructions on the command line ZERR, Z-E-R-R. We're going to change that to 8. And another thing I didn't do was the labeling. So let's do that here. We're going to go to mode naming, number sequentially. So for each atom type, we're going to do this. So I'm going to start with B1 over here, B2 over there. We're going to do the same thing for oxygens. So this is O1, O2. Now for the disordered oxygens, just label one. So this is going to be O3 and that's O4. We'll label the other ones in just a moment. And then we do for the carbon, I'll start here, C1, C2, so forth. I'd like to label the non-disordered side first and then work on the disordered side. So again, when you're labeling, there should be some type of organization and pattern to your labeling scheme. So see, this is O3. So then I'm going to label this carbon 20, 21, 22, 23, 24, 25. Now for the disordered atoms, so O3, if you hover over O3, it's part 2, and O4 is part 2. So I'm going to label, and since they're the 65% occupied, I'm going to label them, name them O3, O3A. I didn't spell it right. O3, O3A, and name O4, O4A. And then for O5 and O6, I'm going to name O5, O3B, and usually A I give to the major one if they're a little bit higher, B I give to the minor one. And we're going to name O6, O4B. There we go. And then for C23, we're going to label it, it's part 2. So we're going to label it the A because it's the major, you know, so it's going to be C23A, or label C23, C23A, and name C26, C23B. That's how we know that, okay, those atoms are disordered atoms, or the same atom but over disordered position. And then we're going to click refine. And then we can do another checksif file as well. So we do another checksif. We'll see that that C error that was related to the Z value will be gone as well. So now we have the checksif. We did another checksif report. Now our Z value is correct. We only have some alert level C and G errors. You know, for example, not that it's very important, but here we have a Hirschfeld difference between C20 and C23A. So maybe we have to go back and kind of model that disorder a little better, but this, you know, G error, it's okay. It's not a major problem with the structure. And so we're good. The checksif works. No major systematic errors with the structure. And so that's modeling this disorder in this ring here. And so now all we have left to do is we just have to draw the molecule. So again, the draw, you know, the draw arrow. And usually I like to draw it with the non-hydrogen atoms. And you see here the labeling is quite big. So what you can do is if we delete all the labels, go to bitmap images and maybe make the font a little bit smaller, maybe 12, and then go non-H. So now it's easier to manage the labeling. And so you see you have O4A, O4B, O3B, O3A. So now someone can see and understand the disorder in the structure. And then once you rearrange all the labeling, so if you hold the shift button, you can drag the label around. And then when you're ready, you just hit go and you can create your JPEG of the asymmetric unit. Likewise, you can type pack and it'll show you the packing diagram. So let's look at that real quick. So remember, pack is packing, and then MATR, and 1 shows you down the A axis. So you have these like channels that are kind of perpendicular to the A axis. So let's try MATR2 down the B axis, and MATR3 down the C axis. That's a pretty neat looking packing diagram. So that's all with this structure. So hopefully you're able to see how to model disorder found in atomic positions. So this is positional disorder in this structure. Dr. Armand signing off.